Consider what happens when you let go of something. It falls, simple, automatic, unremarkable. You've seen it happen thousands of times. But what you're witnessing in that moment isn't exactly what you think it is. You're not watching a force pull an object downward. You're watching something far more elegant. You're watching an object follow the natural geometry of reality itself. Gravity shapes every moment of your existence. It holds the atmosphere around Earth. It guides our planet's path around the sun. It governs the slow dance of galaxies across billions of light years. And here's what changes everything. Gravity isn't actually a force at all. It's the curvature of spacetime itself. For over 2 centuries, Isaac Newton's equations described gravity beautifully. In 1687, he showed that the same mathematics explaining why an apple falls also explains why the moon orbits Earth. Revolutionary. He unified the heavens and earth under one set of laws. His equation was elegant. Every object attracts every other object with a force proportional to their masses and inversely proportional to the square of the distance between them. Newton's laws worked magnificently. They predicted planetary motion with stunning accuracy. They explained ocean tides. They allowed astronomers to discover Neptune in 1846 by calculating where an unknown planet must be to cause irregularities in Uranus's orbit. They pointed their telescopes at that spot, and there it was. But there were whispers of trouble. Mercury's orbit precessed slightly more than Newton's equations predicted. Only 43 arcseconds per century. Incredibly small, yet real. Scientists searched for explanations. Perhaps an undiscovered planet called Vulcan was tugging on Mercury. It didn't exist. Perhaps Newton's laws needed adjustment. Nothing worked. The mystery remained unsolved until 1915, when Albert Einstein published his general theory of relativity. Einstein's insight was radical. Gravity isn't a force. It's the curvature of spacetime itself. Space and time aren't separate. They're woven together into a 4-dimensional fabric called spacetime. Not just mathematical abstraction, physical reality. When you move through space, you move through time. When time passes, you move through spacetime. Every event in the universe happens at a specific location in spacetime, not space and time separately. And spacetime isn't rigid. It's flexible. It curves. What causes it to curve? Mass and energy. Any object with mass or energy curves the spacetime around it. Earth curves spacetime. The sun curves it more dramatically. Even you curve spacetime. Imperceptibly small, but real. Think of a bowling ball placed on a stretched rubber sheet. It creates a depression. A marble rolled nearby doesn't travel in a straight line. It curves toward the bowling ball, following the slope. From the marble's perspective, it's following the straightest path available. But because the sheet is curved, the path bends. Similarly, Earth curves spacetime. When you drop something, it isn't being pulled by a force. It's following the straightest possible path through curved spacetime. The path happens to curve toward Earth's center. The analogy has limits. The rubber sheet is two-dimensional, bent in a third dimension. Spacetime is four-dimensional, intrinsically curved without bending into anything else. But the image helps. In curved spacetime, objects follow geodesics, the shortest paths between points in that curved geometry. A planet orbiting the Sun isn't being pulled by a force. It's following a geodesic through the curved spacetime created by the Sun's mass. The planet is constantly falling toward the Sun, but moving sideways fast enough that it keeps missing. Perpetual freefall. This explains why astronauts in orbit experience weightlessness. They are not beyond Earth's gravity. At the International Space Station's altitude, roughly 400 kilometers up, gravity is still about 90% as strong as on the ground. The astronauts feel weightless because they're in free fall, following a geodesic through curved spacetime. Earth curves spacetime, and the station follows that curvature, constantly falling toward Earth, but moving sideways fast enough to keep missing. You experience the same thing when you jump. For that brief moment in the air, you're in freefall. You're weightless. You don't feel your weight pressing on your feet. The moment is too brief to notice, but if extended, you'd feel exactly what astronauts feel in orbit. Einstein called this the equivalence principle. Free fall in a gravitational field and floating in deep space with no gravity are indistinguishable experiences. Similarly, standing on Earth's surface and accelerating in a rocket in deep space at 9.8 meters per second squared feel identical. The equivalence principle leads to strange predictions. Time passes at different rates depending on where you are in a gravitational field. The stronger the field, the slower time passes. Time actually runs at different rates, not just perceptually. Put two synchronized atomic clocks at different altitudes, and when you bring them together, they show different times. The one in the stronger gravitational field shows less time has passed. This has been measured countless times. In 1971, scientists flew atomic clocks around the world on airplanes. The clocks that flew were ahead of identical clocks on the ground by exactly the amount general relativity predicted. GPS satellites must account for time dilation, or their position calculations would be off by kilometers within hours. Every time you navigate with your phone, you're relying on Einstein's predictions. General relativity also predicts gravitational lensing. Light follows geodesics through curved spacetime. When light passes near a massive object, its path curves. The object acts like a lens, bending light. First observed in 1919 during a solar eclipse, astronomers photographed stars near the sun when solar glare didn't overwhelm starlight. Stars appeared displaced from their known positions. The sun's gravity was bending starlight, making stars appear in slightly different locations. The displacement matched Einstein's predictions precisely yet again. This observation made Einstein a world famous overnight. Today, gravitational lensing is standard in astronomy. Light from distant galaxies passing near massive galaxy clusters gets bent, sometimes creating multiple images of the same galaxy or stretching it into arcs and rings. By studying these lensed images, astronomers map mass distribution, including dark matter, which curves spacetime but emits no light. Black holes represent the most extreme curvature of spacetime. A black hole is a region where spacetime is so severely curved that nothing, not even light, can escape. The boundary of no return is the event horizon. Cross it, and all paths through spacetime lead inward. There is no way out, not because something pulls you in, but because spacetime itself is curved so extremely that all geodesics point inward. Black holes form when massive stars collapse at the end of their lives. A star balances gravity, which is trying to compress it against pressure from nuclear fusion pushing outward. When fusion stops, gravity wins. If the star is massive enough, more than roughly 20 solar masses, the collapse doesn't stop. The star compresses into a singularity, surrounded by the event horizon. For a black hole with the sun's mass, the event horizon would be about 3 kilometers in radius. For a supermassive black hole with 1 billion solar masses, like those at galactic centers, the radius would be nearly 3 billion kilometers, larger than Saturn's orbit. Black holes aren't completely black. In 1974, Stephen Hawking predicted that they emit radiation due to quantum effects near the event horizon. Particle-antiparticle pairs pop into existence near the horizon. One falls in, the other escapes. The black hole gradually loses mass and shrinks. Black hole evaporation. For large black holes, this takes an incomprehensibly long time. A solar mass black hole would take 10 to the 67 years to evaporate. The universe is only 13.8 billion years old. Gravitational waves are ripples in spacetime itself, produced by accelerating masses. Einstein predicted them in 1916, but thought they'd be too weak to detect. In 2015, LIGO detected gravitational waves from two black holes, 29 and 36 solar masses, colliding 1.3 billion light-years away. They merged into a single black hole of 62 solar masses. 3 solar masses converted entirely into gravitational wave energy. In a fraction of a second, this merger released more energy than all the stars in the observable universe were emitting in light at that moment. The detection confirmed Einstein's century-old prediction. Since then, dozens of gravitational wave events have been detected, opening an entirely new way to observe the universe. Dark matter and dark energy puzzle scientists. When astronomers measure how fast stars orbit galactic centers, the visible matter can't account for the speeds. Additional invisible mass provides extra gravitational pull. Dark matter. It doesn't emit light or any electromagnetic radiation, but it has mass, so it curves space-time. Roughly 85% of the matter in the universe is dark matter. Dark energy is even more mysterious. In 1998, astronomers discovered the universe's expansion is accelerating. Something pushes space apart, counteracting gravity. Dark energy makes up approximately 68% of the universe's total energy. Dark matter is around 27%. Ordinary matter is only about 5%. We live in a universe where 95% of it is things we don't understand. General relativity describes not just gravity, but the structure and evolution of the entire universe. In 1929, Edwin Hubble observed that distant galaxies are moving away from us. The universe is expanding. Wind the clock backward, and everything was compressed into an incredibly hot, dense state. The Big Bang. Not an explosion in space, but an expansion of space itself. The evidence is overwhelming. Galaxies move apart. The universe is filled with cosmic microwave background radiation, the afterglow from when the universe was only 380,000 years old. The abundances of light elements match predictions from the first few minutes after the Big Bang. The universe began roughly 13.8 billion years ago. Before that, there was no before in any meaningful sense, because time itself began with the Big Bang. Asking what came before is like asking what's north of the North Pole. General relativity has been tested in countless ways over the past century. Mercury's precession, gravitational lensing, time dilation, the orbit decay of binary pulsars, gravitational wave detection, images of black hole shadows. Every test confirms Einstein's theory. Yet we know it's incomplete. It's incompatible with quantum mechanics. Quantum mechanics describes the microscopic world. General relativity describes the macroscopic world. Both work brilliantly in their domains, but when you apply both to the same situation, like the interior of a black hole or the first instant of the Big Bang, they give contradictory answers. We need a unified theory of quantum gravity. Despite this, general relativity remains one of the most successful theories in science. It revolutionized our understanding of the cosmos, and it comes from a simple but profound idea. Gravity isn't a force. It's the curvature of spacetime. Consider your current experience. You feel weight. The floor pushes up on you. General relativity reveals something subtle. The floor exerts electromagnetic forces resisting your body's natural tendency to move along a geodesic toward Earth's center. What you interpret as weight is the sensation of this resistance, not a downward pull. If the floor vanished and you started falling, you'd feel weightless. Not because gravity stopped, but because you're now free to follow your geodesic. Freefall is your natural state of motion in spacetime. From spacetime geometry's perspective, freefall is natural. Weight is abnormal, caused by something pushing on you. This explains why all objects fall at the same rate in a vacuum, regardless of mass. Galileo demonstrated this. Apollo 15 astronauts dropped a feather and a hammer on the moon simultaneously. Both hit the ground at the same time. In general relativity, this makes perfect sense. Objects aren't being pulled by a force proportional to their mass. They're following geodesics through spacetime. The curvature doesn't care about mass. All objects follow the same geodesics. At Earth's scale, gravity shapes everything. The atmosphere exists because gravity holds it in place. When Earth was molten early in its history, gravity sorted materials by density. Iron and nickel sank to form the core. Lighter materials rose to form the mantle and crust. Gravity drives plate tectonics through mantle convection. At the solar system scale, the Sun's gravity dominates. It contains 99.86% of the system's mass. Planets follow elliptical orbits, geodesics through the Sun's curved spacetime. Jupiter's gravity creates gaps in the asteroid belt through orbital resonance. Saturn's rings show similar effects, with small moons shepherding particles. At stellar scales, gravity creates and destroys. Stars form when dense regions in molecular clouds collapse under their own gravity. As material falls inward, gravitational potential energy converts to heat. Eventually, the core reaches millions of degrees and fusion ignites. The star shines steadily, balancing inward gravity against outward pressure. When fusion stops, gravity wins. The core contracts. For massive stars, this triggers a supernova, scattering heavy elements into space. Every element heavier than helium in your body came from stellar fusion and supernova explosions. Gravity made those stars, crushed their cores, triggered the explosions, then brought scattered material together to form new stars and planets. Neutron stars are among the most extreme objects, roughly 1.4 solar masses compressed into a sphere only 20 kilometers across. Density approximately 400 trillion times that of water. Surface gravity is 200 billion times Earth's. Some spin hundreds of times per second, emitting radiation beams from their magnetic poles. As they rotate, these beams sweep like lighthouse beams. If aimed at Earth, we see pulsars, nature's most precise timekeepers. Galaxies are also held together by gravity. Not solid objects, but billions of stars gravitationally bound. The Milky Way is roughly 100,000 light years across, containing 200 to 400 billion stars. All orbit the galactic center. Our Sun takes about 225 million years to complete one orbit. At the center is a supermassive black hole, Sagittarius A, with a mass of approximately 4 million solar masses. Astronomers have tracked stars orbiting it. One star, S2, reaches speeds of around 2% of light speed at its closest approach. The Event Horizon Telescope imaged the glowing gas around Sagittarius A, revealing the black hole's shadow. On the grandest scales, galaxies arrange in filaments stretching across space with voids between. This cosmic web structure grew from tiny density variations in the early universe. Slightly denser regions had slightly stronger gravity, pulling in more matter, becoming denser, amplifying over billions of years into the architecture visible in galaxy surveys. The universe's expansion is accelerating. In the far future, galaxies beyond our local group will be pushed beyond our cosmic horizon. Eventually, in trillions of years, only galaxies gravitationally bound to our local group will remain visible. The rest will have been carried away by expanding space. Space exploration faces fundamental limits. The nearest star is over 4 light years away. Even at 10% of light speed, far beyond current technology, the journey would take over 40 years. The speed of light is the speed of causality, the speed at which information propagates through spacetime. General relativity tells us the universe operates on scales far beyond human comprehension, placing fundamental constraints on what's possible. Yet there's beauty in this. Understanding general relativity changes how you see reality. You live in a universe where space and time are unified into spacetime. Spacetime is flexible, curved by mass and energy. You are not held to Earth by an invisible force. You're following the natural contours of curved spacetime. When you drop something and watch it fall, you're not seeing a force pull it down. You're seeing it follow the natural geometry of spacetime. When you look at the moon, you're seeing an object in freefall, endlessly circling Earth, because that's the geodesic it follows through curved spacetime. Mysteries remain. Dark matter and dark energy, quantum gravity, black hole interiors, but general relativity provides the foundation. The core insight that gravity is spacetime curvature will endure as fundamental truth about how the universe works. You're not being pulled down by gravity. You're following a geodesic. You're surfing the geometry of the cosmos, part of a vast dance that's been going on for 13.8 billion years and will continue for trillions more. The universe is vast and complex, but it's also comprehensible. We can figure it out. We are figuring it out. And that should fill you with quiet wonder.